Uh, can you see that?
Yep.
Okay, good. Right. So with regard to that last question, right? Both carbocations and alkenes. They're both stabilized by what we would call hyperconjugation. So that's a commonality between the two of them. Carbocations are also stabilized by inductive effects. The alkenes, though, if you do an analysis of, let's do this. Oh no, I'm gonna drop this other way. Okay, so. So if we do, sorry, it was just muting. If we were to look at, so both of these have got 1, 2, 3, 4 carbons. Both of these got 4 carbons, and there's 1 pi bond. So they're basically constitutional isomers of one another. Now, if I was to point out to everybody, I should have had a top hat question for this. This sigma bond here, what are the 2 hybrid orbitals that make up this sigma bond? So carbon A is using something, carbon B is using something else. Right, carbon A is using an sp2, carbon B is using an sp3. And so this bond over here, if we were to call this A primed and B primed, again, A primed would be using an sp2, B primed would be using an sp3. Because remember, sigma bonds are made with hybrid orbitals. Now, if you look at the constitutional isomer over here, let's use a different color just because we should. Purple, A, and B. Again, A will be using sp2, B will be using sp3. Now, if I put C over here, what orbitals are being used between B and C? sp3, right? So B is sp3, C is sp3. Because they're both tetrahedral, so they're using sp3 hybrid orbitals. Now I'm going to ask you a bond strength question. Which bond is stronger? So these are both sigma bonds. Sigma bond made of sp2, sp3, or a sigma bond which is made from sp3, sp3. And we'll call this scenario 1, and we'll call this scenario 2. So which one is stronger, 1 or 2? Okay, so the majority of the answers is number 1 is stronger, and that is correct. Okay, so why? Okay, so it's true that double, okay, so, okay, but we're not talking about, these are both sigma bonds. So it's not a bond, it's not actually a pi bond here, it's a sigma bond. So it's true that double bonds overall are stronger than a single bond, but a sigma bond is stronger than a pi bond, right? So okay, right. So sp2 has more S character. And why is this important? So if an sp2 bond has more S character, an sp2 bond is going to be shorter. The so, and whenever like, remember in Gen Chem 1, and it might have been done in Gen Chem 2, when we did that whole analysis of bond lengths, and the shorter the bond, typically the stronger the bond. So anytime you've got, so if an sp2 hybrid orbital has more S character, it's going to be shorter. And that means it's going to be, when it's shorter, it should be a stronger bond. So, and if we'll look up we could probably look up the energies. We could find the energies of the various between an sp3 bond versus an sp2 bond. And you'll see that the distance between the nuclei would be shorter, and the bond strength, the actual energy between the two, is going to be stronger. So when we're looking at a scenario between these two constitutional isomers, both of these bonds, which I'm highlighting in purple here, are going to be shorter and stronger than, say, this bond over here on the right. So overall, it's going to be lower in energy. So it's going to have, and so will make it more thermodynamically stable. So there are, of course, some like steric things become important later on, but that's only for comparing apples to apples, not apples to oranges. So yeah, so with carbocations, they're stabilized by hyperconjugation and inductive effects. With alkenes, they're basically stabilized by hyperconjugation, and there's this built-in thermodynamic stability for the bond strengths. So the more substituents, thermodynamically, the lower the energy would be. So that was basically a couple of the things that were on the introduction part of the alkene part. What we're going to talk about next is alkenes. Basically, before I actually move on to that, were there any questions on that?
Sorry, are we calling this an inductive effect? I wouldn't think so.
No, like the bond strengths, that's more a thermodynamic effect. So inductive effects would stabilize carbocations by pushing electron density to that empty p orbital.
Yeah, so what are we calling this?
So this is just like a bond strength analysis. It's like a thermodynamic stability due to bond strengths.
Okay, so the one on the left is more stable than the one on the right, is what we're trying to say?
Right. So if we were drawing an energy diagram, and let's say that there was some sort of possibility of, there was some intermediate and you could make two products. One would be here and one would be here. So this would be this one, and this would be that.
Is that for breaking the same bond, sorry?
No, this would be if there was some option to make either one of these two. like for example, you can isomerize bonds with strong acid, right? So on an energy diagram between the two of these, this was free energy. Gibbs. Free energy. There would be some sort of equilibrium set up. And the one on this one would be lower in energy. This one would be higher in energy due to the bond, basically to those bond strengths.
Okay, so if on the left one we had it so that it was a methyl instead of an ethyl group, I guess.
Okay.
That would be more stable than the ethyl group. Just ignoring the one on the right completely.
Okay, no, when we're doing an analysis like this, you basically have to have the same number of atoms associated with it.
Okay.
Because
Okay,
if we're comparing, say, this versus this,
yeah,
that's it. That's not really. You basically have to compare apples to apples.
okay, that makes sense. Thanks.
Okay. The question about this was just a generic question about pi bonds if it was made up of a hybrid orbital of sp2 and sp3 versus sp3 and sp3. That's what that question between 1 and 2 was. And because an sp2 orbital has got more s character, the bond length is going to be shorter, and shorter bond lengths correspond to stronger bonds if you're comparing carbon-carbon bonds to carbon-carbon bonds. So that's what this question here was about. Okay, now, so what the important thing for the next chapter on our journey is going to deal with alkenes. And what we're going to see is that the feature that they've got is this carbon-carbon, this pi bond. So the electron density is both above and below the sigma bond. And what we're going to see is that alkenes are going to behave as nucleophiles. And so they are going to be, the electron density of these pi bonds is basically going to, let me get a different color here, be used to attack an electrophile of some flavor. And alkenes are going to be doing, so if you have one molecule and you react it with another molecule to make one molecule, these reactions are called what type of reaction? 1 + 1 = 1. Addition reactions, right. So additions. So addition reactions. And their alkenes are going to be reacting with electrophiles. So overall, what these are going to be called is electrophilic addition reactions. And so the fun part is that it's just going to be history repeating itself over and over and over again for how these work. So there's a whole series of potential reactions that we can do. So I'm going to draw this like a little double bond like this. And we can add a whole series of different electrophiles. So the one we talked about earlier in the day was if we react an alkene with an acid, so like so X equals Cl, Br, iodine, like one of these strong acids, what we're going to see is that the acid is going to be added to the double bond. So we are going to make this type of compound here. So the carbon on the end, we'll label as A here, it gets the proton, and carbon B here, it gets the X. And we're going to see why in a second. So the first class of reactions is basically going to be an electrophilic addition reaction using the various acids. We are going to do something very similar with water. So in which we're going to actually, I'm going to put water in quotation marks here, because the overall effect is going to be the same as adding hydrogen to one carbon and the hydroxyl group to the other. So we're going to do one class of reactions which is exactly the same, in which the OH goes on carbon B and the H goes on carbon A. Or there's another set of reactions we can do, which is going to be exactly the opposite. So we're going to put the OH on carbon A. So that's another possibility. We can also do a reaction where we're adding hydrogen gas to each one. This is maybe a little less interesting because all we're going to do is convert the double bond to a single bond, and we're effectively adding hydrogen to each carbon. This is what we would call a hydrogenation. And this is what they do with certain fats when they're converting them into hydrogenated fats. So they take a fat which is unsaturated, which has got double bonds, to do a hydrogenation reaction to make a hydrogenated fat, which is all single bonds. And they typically do this for preservation to make it easier to use, like for food and that sort of stuff. So that's this process here. And there's a whole other bunch of things that we're going to see. We're going to see that you can add, XX. So we're going to add 2 halogens to each carbon. This would typically be bromine, because it's the easiest one to work with. And then we're going to do adding XOH. So we can have adding OH to one carbon and X to the other. And what else are we going to do? We're going to do one where we add OH to each carbon. So we're going to have OH here and OH here. So there's a whole series of different reactions that we're going to do with alkenes, but all of them are going to be similar in nature in the fact that the double bond is the nucleophile, and what it's going to be reacting with is an electrophile. So that's the joy of what we're going to be talking about in the coming days, I guess. But the one we'll start off with first is adding HX. because it's basically it's going to basically show how this whole all the process works. Each one of these is very similar, but the HX one is the best place to start because it's easier to understand because it's going to follow the fundamentals of what we've learned before. But yeah, most of these are electrophilic addition reactions. They're all very similar. And we're going to use some really interesting and novel reagents for some of them. It's going to be great fun. So let's talk about the addition of, addition HX. Okay. So we did this, and I'm going to use this as our reagent here, plus HBr. Okay, so in the preview, we saw that HBr is the electrophile. And we are going to use the pi electrons in our double bond to attack the electrophile. So the delta positive end is, of course, the bromine, is the proton. So if we were drawing an arrow to show how this reaction works, we would draw it like this. So the pi bond is attacking the proton, and then the electrons in the hydrogen bromine bond are going to move on to the more electronegative bromine. So there's basically two different ways that this could happen. And I'll give you just a little, I'll draw it over here as well. And you're going to tell me which way is the best way. So let's just do this exactly the way. This is polarized like this, and we'll get out our, use green this time. So there's two potential intermediates here. The first would be this. And the second would be this. Okay, so if we remember our drawing protocols for skeletal drawings, we don't draw protons when they're attached to a carbon, right? So this carbon here now has the proton from the reaction, and this carbon here has the proton from the reactions. We don't draw it on there, but the other carbon is now, because we're missing those electrons, is now a carbocation, so it's got a positive charge. I'm just going to erase this little circle here. So, and if we count our carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So it's consistent. There's 5 in each one. There's a methodology which organic chemists use when they're drawing mechanisms for an attack of this fashion. So the arrow, which is coming off of the double bond, if it loops, let me get out my little laser. Oh, it doesn't work on this thing. Okay, I guess that's, I'll just go back to what I was doing before. If it loops towards, like this green arrow here, it's looping back towards the carbon which I'm placing the proton on. So I placed the proton over here on this carbon. That's why it loops back towards that. It's basically saying whatever's attacking is going on that carbon. Where the blue arrow up here, it's going towards this carbon here. That's why this carbon over here got the proton. So whenever we're drawing mechanisms, you basically loop the arrow back towards the carbon which is getting that, whatever you're attacking. So we've got two products here, and you're going to tell me which one is the better one. Should we form A, or should we form the intermediate B? And why should we be forming one of them over the other? Right, it is. So everyone's basically said A, and the answer is because A is a more stable carbocation because it's secondary. This is a secondary carbocation. This guy's a primary carbocation. Secondary carbocations are more stable because of hyperconjugation, and there's more alkyl groups, right? More substituents. So, right. So when we're doing this electrophilic addition reaction of HX, the first step, the pi bond is going to attack the electrophile, which in this case is the H plus. And it's going to attack in a fashion which produces the more stable carbocation. So this second thing down at the bottom, this part here, this doesn't happen. Whoops. This doesn't occur. It is the first part which is taken place. So this is the one which is the correct way of working, because you're going to form the most stable carbocation. If we were drawing an energy diagram of this, and I'll draw it down here, the first, so reaction coordinate, free energy, starting material here, our double bond, and it's going to go up in energy. We'll call this A. If we wanted to go to B, this energy would have been B. Because B is a primary carbocation, it's going to be higher in energy. So the lowest path will be to form the carbocation A. Now, the next step, now I'm going to ask another question here, is that, okay, I'm missing a negative charge on my bromide. So let's put that on there. So the second step in this mechanism, which fragment is the nucleophile now? Right, so this guy here is now the electrophile. This is the nucleophile. And so the second step will be bromine attacks, and we are going to have our final product, which is this molecule here. So this will be our final product. So you've effectively added H to one carbon, A, and we've added Br to carbon B. So it's basically a two-step process. First, you form the carbocation, the most stable carbocation, and in the second step, the bromide now becomes a nucleophile and attacks. So which step do you think would be faster? The first step or the second step? Right, second step is faster. So on our little energy diagram here, there would probably be a very small little hump here to get over, and then you would form your product. So we'll just erase this little bit right here. So the first step will be the rate determining step. You're forming a carbocation, which is pretty high in energy. So the second step would be faster. The first step would be the rate determining step. Okay, good. Now, so let's do a couple of examples. I drew that poorly. And okay, so take a couple of seconds. This is normally would be when I walk around the classroom and look over everybody's shoulder. But take a couple seconds and draw out what you think the products are here for each one of these reactions. I guess I should have mentioned. Okay, so this rule, and I guess once we do these reactions, I'll come back to it but let me know when you've gotten some answers to these questions. Yeah, one of the things that I used to do in class was I could get everybody to pass their paper to their neighbor and have their neighbor mark them, just for fun. Oh, the joys. Next year, perhaps that will happen. Okay, so one of the things that's one of the little rules that the rule for this type of reaction where we've got where you form one constitutional isomer over another. This is basically, this rule for this is called, we get to an open space here. It's called Markovnikov's rule. So with Markovnikov's rule, you basically form the most stable carbocation, and the final product is based off of that. So if you've got a double bond, the easiest way to, or actually, let's just erase this for a second. Put this R. If protons equal money, the rich get richer. So this is how I've basically explained it in the past. So if you're looking at it, if you're looking at the double bond, basically divide it in two and decide which carbon has got the most protons, because whichever carbon's got the most protons, if you equate that to money, the rich will get richer in this reaction. So the carbon over here, which this one's got two H's, this one's only got one H. So if this was reacting with, say, HBr, the rich get richer. So the carbon with the R will have the Br. We'll call this B. Carbon A gets the proton. So Markovnikov's rule, the rich get richer. So, and yeah, that's basically, and it's based upon the carbocation stability, which carbocation is the most stable. So if we're looking at our three reactions here, call this carbon A, we'll call this carbon B. Carbon B has got no protons, carbon A's got two. So if the rich get richer, carbon A is going to end up with the proton, carbon B is going to end up with the chlorine. So we will make this compound here. So CH3, methyl group, and the chlorine is going to be on the carbon B. In the second reaction here, we will have carbon A, carbon B. Carbon A's got one proton, carbon B's got none, so the rich get richer again. So CH3, Br, and carbon A, which we'll draw here, has got the proton, but we don't need to draw the proton because in skeletal structures, we just don't draw the proton. Now, what about carbon, this one here, reaction C? Call this A, call this B. What do we do in a case? Okay, I got a question here. Okay, so far, none of these, there's a plane of symmetry for the products for all of these molecules. There is no enantiomer for reaction A or B yet because of the symmetry. Because there's basically, it would go, the plane of symmetry would go right through here and then bisect the methyl and the chlorine. Same with this one here. There is no plane of symmetry there. Later on, the answer is yes, we're going to make two. We'll do an example of that just in a second here. Okay, so with carbon C, with molecule C here, which carbon should get the proton, A or B? Right, both of them should be the same, right? So our product here is going to be, so we'll draw I on carbon B. We'll draw I on carbon A. And what's the relationship between these two molecules here? What are they? Are they enantiomers, diastereomers, constitutional isomers? What are they? They're identical, right? So this molecule's got symmetry, so they're identical. Okay, good. So, but actually, this the question which was brought up earlier. Let's pretend that let's go back to our original compound here, and react this with HCl. So carbon A has got 2 protons, like carbon A's got 2 protons, carbon B's got 1, so the rich get richer. So we would technically make this product here, and this would be a mixture of 2 enantiomers, right? Because this carbon here is now chiral, because you've got methyl group on one side, ethyl group on the other, chlorine plus the hydrogen, which we haven't drawn. So these reactions, if you do form, they do have a possibility of making 2 enantiomers. So you would make a mixture of the two, because you've got a carbocation and the nucleophile can attack, like this nucleophile up here, which at the very start, over here, this bromide could attack from the top or the bottom. So you'd actually make just two different possibilities here. So, okay, good. So how did everybody, so before I move on, how did everyone do with these reactions? Excellent. Okay, so we got a whole bunch of goods. Okay, that's what I want to hear. Now, here's an interesting, let's do one more question here. There is one more little tidbit I guess I should bring up. Okie dokie. So okay, when chemists were doing this reaction here, they found that, okay, so if we're doing our typical analysis of our 2 carbons here, carbon A has got 2 protons, carbon B has got 1. So if this reaction is to take place, the rich get richer. So this pi bond should attack this proton, and the chloride will leave. So our intermediate would look like this. Oops. And then chloride can come in and it will attack. And this will give us our product. Call this A. And CH3, Cl, H, H methyl. We'll call this product A. Now, it turns out that they also found another product here. And the product that they found was this one. And I'm curious to know how this one here formed. How did we end up with this interesting compound here? Okay, good. So to make this product here, this would come from if we had a situation like this. Positive charge. And then our chloride, I'll color this in blue, came and attacked, right? So we'll call this B. So to make product B, you need to have a carbocation on this carbon here. And so there are, if we remember from last term, there was a way you could do this where you would have the rearrangement of a carbocation. Okay, so first question is, why would carbocation here, we'll call this carbocation 1, why would it rearrange to carbocation 2? Right, it's more stable because carbocation 2 has got 3 alkyl groups attached to it, whereas carbocation 1 has only got 2. So when they were doing these, like the initial investigative sort of studies on these type of reactions, these electrophilic addition reactions of strong acids, in certain instances, they would see these shifts happening. So we would call this, because what we actually are doing is we need to put this little hydrogen, sorry, I shouldn't say, wait a second, where's my draw? This hydride needs to move to there. So this is actually what we would call a hydride shift. So it's taking those 2 electrons in that sigma bond and it's moving over and it's forming a more stable carbocation. So when we did these electrophilic addition reactions, you could do hydride shifts and you could also do methyl shifts. So we could rewrite this entire reaction, but replace that H with a methyl, and they found a similar result. So it's one of the, it's part of the evidence that suggested that this is exactly what how this whole thing works is consistent with carbocation stability and stuff, that in fact there is a carbocation intermediate and you form the most stable carbocation, and it is and that's how the whole Markovnikov. Okay, so there's a hand being raised. Now, where do I see this? So yes.
Yeah, sorry, what causes the hydrogen to move? I understand that it makes sense, but what are the electrons doing?
Okay, so right, let me try to draw that. Okay, so let me expand this a bit. So if we had, I'll just call this R and I'll call this H. So these two, the electrons in this bond are basically moving together. If I was drawing this as a, like trying to draw this as an intermediate, like a transition state, it would almost be like if I had a partial bond to an H and a partial bond to an H, and H, R. And so this would have a delta plus, and this would have a delta plus. And once it's moved over, then this would be, this carbon here would be the, would have a carbocation there. So it's basically, it's a hydride shift because a hydride is H with 2 electrons, right? So it's using the 2 electrons in this sigma bond to basically hop over. I don't know how better to describe it.
No, that makes sense. Thanks.
So it's not, this isn't a resonance structure because we're actually changing the connectivity of the atoms. It's not a resonance structure because we're not only moving electrons, we're also moving actual atoms. So it's and the bond that we're actually breaking is a sigma bond. So it's, we're breaking like a sigma bond to do this. So yeah, the first reaction is basically the addition of HX, HBr, HCl to a pi bond. Now, right, and what we're going to see actually a bit later on. So if we've got this molecule here, and we react this with HBr, as we'd shown before, we are going to make this. And we are not going to make this. Because the rich get richer. Later on, what we're going to see is I'm going to show you a way how to make that through a completely different type of, completely different mechanism. But for all, like, chemists love to be able to do, if there's a possibility of doing A, there's somebody out there who wants to do B, right? So it's one of those things that for all of these various reactions, because at some stage you're going to need to do the other one. So yeah, we call these types of reactions where you could make 2 different constitutional isomers. We call these reactions regio selective reactions, where you're going to make one constitutional isomer over another one. And yes, so one of the things that that you guys learned how to do in Organic 1 was you knew how to make this reaction, and you also learned how to do this reaction, right? So if you want to make the double bond, which is the least substituted, you did A, and if you wanted to make the double bond, which was more substituted, you did B. And so there's similar sort of things going the opposite direction. So what base did you use to make in circumstance A, and what base did you use to do B? Because these are elimination reactions, right? So for A, you would use, so these are elimination reactions, so you want to use like a strong base. For A, you would use the large bulky base. For B, you would use a smaller base, right? So we could use, say, tert butoxide, tert butanol. And for this, we might use methoxide and methanol, something like this. So Hoffman product and the Hoffman Siev. I'm missing a Z in there. So yeah, these types of, so we're going to see later on that you can do addition reactions and do it, do regioselective addition reactions later on. Okay, so what we're going to do next, because it looks like we're out of time, what we're going to do next class is we are going to do, I think the next one we will do is the addition of, I think we'll do BR2 next, or X2. We'll start there, and then we'll do the addition of water, and then we'll do the hydrogenation reaction. I think that's the order. We'll do the BR2 one next because it's interesting because it's similar in the fact that we're going to form a carbocation type intermediate, which is going to be slightly different. And the neat part of that is that there's no X there, right? I mean, there's no H there. It's just, so it's the molecule it's attacking is symmetrical. So you're not necessarily worried about which carbons gets the H and which one gets the X. This one, they're both going to get the X, but the intermediate's really important, and it's going to basically influence some of the other reactions we do after that. So it should be fun. But that's basically what we covered today. Any questions at all?
Yeah.
Okay.
So for the hydride shift, would the methyl shift be less likely in that compound in particular because the carbon is, because it's the shift is determined by the relative electronegativity. Is that right?
Okay, so in this, like in the example we had here, there wouldn't be a methyl shift because, okay, so let's redraw this. Okay, carbon. So the compound we had was the one on the right here. So if, like in the one on the right here, if you move this hydride to here, we're going to make a tertiary carbocation, which will be more stable because this is going to give us carbon CH3, CH2, CH3 positive. So if we were to try to do a methyl shift in this instance here, like let's say we moved a methyl over, we're going to be making a secondary carbocation. So it's not helpful. It's going to be basically relatively the same energy. When I said that there could be a methyl shift, what I meant was if there was molecule, this sort of guy here, where there's a methyl next door and it moved, and then you're still generating a carbon you're still generating a tertiary carbocation. So the similarities between the two here, tertiary carbocation, more stable. Tertiary carbocation, more stable. But like this intermediate here, which I'll circle it in gray. This one here, yeah, it's the hydride shift which would generate the more stable carbocation. It wouldn't be a methyl shift because you would just be you'd be going from secondary to secondary, which isn't, it's the same energy, right? So there would have to be something. That's not impossible, but there would have to be something which is promoting that to happen. Like if there was a ring structure where there was a certain amount of strain associated with the ring, and you could expand it because you're releasing ring strain, or there's some sort of steric strain, then that might help. So you could go from secondary to secondary, but for most cases, it's like what we're dealing with, it would be purely based on going from a secondary carbocation to a tertiary carbocation, something like that. But when it comes to if a question like about a hydride shift or a methyl shift was taking place, I would typically ask this in a mechanism question, not necessarily in a reaction question. Whenever we're doing reaction questions, I'm usually not thinking 2 steps ahead, which would be for a hydride shift. It's more, this would mainly be a mechanistic question, like you make this strange product, explain why, right? Okay, were there any other questions at all? Okay, if not, then super. So what we'll do is on Tuesday, we will come back and it's going to take a couple of lectures to get through all these addition reactions, but we'll start off with the addition of alkenes and halogens, specifically Br2 because it's a nice red liquid and it's easy to manipulate. So that's where we'll start off. But until then, if you have any questions at all, just send me an email and stay safe over the weekend.
Thank you.
And enjoy your other classes too. And I'll post this lecture on Top Hat over the next couple hours or so. Alrighty, so I will stop.